Next speaker and the last one of this session, this first half of my morning, is Professor Delphine Farmer, and she is an associate professor at in the Department of Chemistry at Colorado State University. And she's going to be talking about outdoor particulate matter sources and the chemical transformations that take place when they interact with the indoor environment. So Delphine.
Great, thank you very much. And thank you to Dr. Stevens and Dr. Ivy for giving an excellent introduction to what I'm going to talk about, which is the sources of particulate matter in outdoor environments, and then what happens when they actually, after they have infiltrated the indoor environment. And this is an interesting topic to me because I've spent most of my career so far thinking about outdoor particulate matter and the trace gases that then react to form that particulate matter in a range of both remote and polluted environments. But then more recently, I've been thinking about what happens in indoor environments. So my perspective on particulate matter and components that really that control them is that we can think about the rate of change in the concentration of any component in the atmosphere. And we can think about it very simply in terms of sources and sinks. So this very simple expression says that the change in concentration of anything that we breathe as a function of time, that concentration, is equal to the production, so the sources, so that includes direct emissions, so primary emissions, like from the tailpipe of a car, as well as chemical sources, so reactions in the atmosphere. So that's our production sources. And then we also remove them through losses, that's chemical reactions, and then wet and dry deposition. And then we have a meteorology term in the outdoor atmosphere, so a term that accounts for moving air around. So this talk is obviously going to be focused on the sources. But before we do that, I want to note that the sinks are also really important. And in fact, this deposition term is really what controls particle lifetime. And it is arguably the most poorly understood component in both indoor and outdoor environments. But this deposition term in outdoor environments tells us something very important. And it tells us that at least about submicron particles, the PM2.5 we're focused on here, that really has an average atmospheric lifetime of about a week, so about 7 days. So any particles that are emitted around the planet have about, on average, a week to move around. And so what that means is that what we breathe, our exposure, is a combination of both local sources and then sources transported from other regions. And these sources obviously vary through time, but they also vary on different spatial scales. And this figure is a lovely image from a NASA model output. And what it shows is that you can see different sources. So dust is in red, and you can see dust from the Sahel moving over the Atlantic towards North America. You can see the storms in the southern Atlantic producing sea spray aerosol. You can see the smoke from the Amazon rainforest, and then you can see sulfate in white, and you should see the emissions from the coal-fired power plants in Asia, as well as some in Europe and in North America, and you see those transporting. And if you have eagle eyes, you will catch that there is a volcano somewhere in here as well. But what I wanted to focus on is this question of smoke. And the reason I want to do that is I don't have time to talk about all of the different sources and different chemical reactions that take place in the outdoor atmosphere. But smoke is a really useful example to think about these processes that control particle sources. So there's this nice study from Dan Jaffe's group in Washington that shows that very, very clearly demonstrates that particulate matter across the United States has been decreasing. And this is really a testament to the Clean Air Act and regulatory activities that have reduced not only primary emissions, those direct emissions, but also chemistry, the other source. And so you can see that most of the United States has had decreases in particulate matter. But there's a hotspot, and there's one region of the continuous United States in the Western US that actually has increasing particulate matter. And this is due to wildfire smoke. And if you look at the bottom figure, this shows sulfate aerosol, so one type. And then the top figure shows carbonaceous aerosol. And what you should see is that it's the carbonaceous aerosol that's really increasing in concentration. And that's because smoke is mostly organic aerosol. And of course, this increase in organic aerosol from biomass burning, from wildfire smoke, is influencing both outdoor air quality and indoor air quality. And in the last couple of years, we've seen particularly compelling examples in the news and personal experiences of many of us that the wildfire smoke is a growing problem. And it's also being influenced by climate change. So I want to dive into wildfire smoke for a moment. And this is because this is something that my group actually studies. We took part in the WeCan project a couple of years ago. And what we did was take an aerosol mass spectrometer and put it on an aircraft and flew into wildfire plumes, very close to the emission source. And then we would fly back and forth and trace that smoke plume as it dilutes. And so we could watch the chemistry. So what I'm going to do is walk through a little bit of that chemistry, and then we're going to use that as a framework to think about what's happening in the rest of for the rest of this talk. So the first thing that obviously happens when you have wildfire smoke emission is that plume dilutes. And so we see very simple dilution, just the concentration decreases. But that dilution tends to impacts the equilibrium of the system. So that organic aerosol that dominates biomass burning emissions has some semi-volatile components. So when you move it from a high concentration region to a low concentration, equilibrium just drives some of those semi-volatile components off. So dilution-driven evaporation. But that's not the only thing. Particles aren't the only component that's emitted from wildfire smoke. We also have lots of trace gases. And so in that plume, as we follow it after emission, we can see that those trace gases can get oxidized. And the oxidation products, for example, oxidized volatile organic compound, can be lower in vapor pressure than their original parent compounds. And then they have a low enough volatility that they condense and partition to that particle mass and form what we call SOA, or secondary organic aerosol. Okay, the last thing that can happen is that if you remember, we had dilution-driven evaporation that released a series of volatile components. Those can also be oxidized and then condense. So Brett Palm at the University of Washington did a really nice analysis of all of the trace gas and particle data that was collected in this project and showed that even within just a few hours after emission, about a third of the particulate matter from smoke was actually secondary organic aerosol. And that the bulk of that was actually driven from that evaporated primary aerosol. So that dilution-driven evaporation then reacting to do chemistry and form SOA. So this should tell you that the atmosphere is a really dynamic environment, lots of chemical reactions, and this is constantly changing the composition and the amount and the size distribution of the particles that are in the atmosphere. Okay, I don't have time to go into the details of all of the amazing chemistry and the recent knowledge we now have on all of the sources of outdoor particulate matter, but I thought I would just put the slide up so we can cover all the bases quickly. So we know that there are anthropogenic sources of primary particulate matter, so the tailpipe of your car, any fossil fuel combustion. We also know that humans are doing things that release those volatile compounds that can then be oxidized through chemistry and form secondary aerosol. And that's volatile chemical products is beginning to be realized as a large source of those components. Agriculture is another. Then we have natural sources of aerosol. So recently in the news, we're hearing about volcanic emissions. Sea spray aerosol is particularly relevant for people who live on coasts. And then, of course, the biosphere is a massive source of volatile organic compound that can also then go on to produce particulate matter. But we obviously have spatial heterogeneity in this outdoor particulate matter. And And I think it's worth thinking about how this links to the chemistry, and that we can't just put all particulate matter into one bucket. And this is a lovely example from a research group in Switzerland. And so using a combination of measurements and models, what this group did is first looked at the concentrations of particulate matter. And this is PM10, so slightly larger size range than we've been talking about in this workshop. But this PM10 concentration obviously is spatial variability. And when this group looked at the sources of particulate matter, they noted that most of the particle concentration was really driven by crustal material, and then secondary chemistry. So inorganic aerosols, so we're talking about agriculture precursors, and then biogenic secondary organic aerosol. But what was really unique about this study is that they were able to couple the concentration measurements to measurements of oxidative potential in the aerosol. And so the DTT assay is one of many assays that provides some metric for oxidative potential. So this is the potential for those particles, if they interacted with a cell in the human body, how might those cause oxidative stress? Imperfect measurements, but useful indicators. And this oxidative potential, if we look at the map, obviously is different in trends from the concentration, but more than that, the drivers of oxidative potential were quite different. And in fact, in Europe, we're driven by anthropogenic aerosols, so wood burning, wood smoke, and then vehicle wear. And what this study really highlights to me is that we need to understand more than just aerosol sources. We need to think about the chemistry and use the chemistry to link to health effects. But of course, as Brent Stevens nicely highlighted, we don't breathe much of our air outdoors. We spend most of our time indoors. So most of the air we're breathing, while it might be derived from outdoor sources, is actually inside a building. And so I want to think a little bit about what happens to the chemistry of the particles when they move from the outdoor atmosphere to indoor air. And we have to think about a few components. We have to think about the very high surface area indoors. We have very low oxidant loadings indoors relative to outdoors. We have very short timescales. So outdoors, we had 7 days to think about chemistry. Inside, with ventilation rates, we're really thinking about minutes to hours. And then, of course, we have a huge array of volatiles in the indoor environment, different gases from all these different sources. So we have a lot of potential chemistry occurring. So what I'm going to do is use the framework we just developed for outdoor wildfire smoke, and we're going to apply it to indoor particles. So we can think about particles upon infiltration in that indoor environment. Now they're experiencing much lower concentrations than they were outdoors. So we can have that same dilution-driven evaporation, and it will actually move condensed material from the outdoor aerosol sources to the indoor gas phase. And we can actually see this in studies from the DiCarlo group looking at indoor-outdoor ratios of different chemical components. And you can see that some of the more volatile components have lower indoor to outdoor ratios. So we need to start thinking about the chemistry of the particles and their partitioning. Now, unlike smoke, we really need to think about temperature gradients when we move particles between the outdoor and indoor environments. So today in Colorado, we just have a light dusting of snow outside, and it is definitely colder. And inside, it's nice and warm. And so when particles infiltrate, undergo infiltration from the outdoor environment into the indoor air, they can then undergo thermal partitioning. So as we warm those particles, they can then volatilize and send components into the gas phase. For those of you who are watching this from Florida or somewhere nice and warm, what you may be seeing is the opposite. Instead, we're going to have moving particles from warm environments to colder environments, where then particulate matter may condense upon them. And so this should hint to you that we expect to see seasonal differences in those indoor to outdoor ratios. And indeed we do. Again, more work from Anita Avery and Pete DiCarlo shows that those indoor to outdoor ratios are higher for most components in the particle phase in summer than in winter. Okay, so that's partitioning, that's dilution and temperature. But now we have chemistry. And so there are other, as I told you before, there's a huge amount of volatiles in the indoor environment. So we can look at everything from cooking to the wood furnishings and the paint and the materials that are used to build houses. Those all emit volatiles. The personal care products and other chemicals that we bring into our home also emit volatiles. And even us, the air that we exhale and then permeating through our skin, we have huge arrays of volatile compounds in the indoor environment. Now, the oxidant levels are low. But if there are oxidants, they can react with this huge amount of fuel, do a series of chemical reactions, and produce an array of oxidized organic and inorganic products that can now condense to form that secondary organic aerosol. And I think Michael Waring is going to talk about this in a little bit, but I just wanted to provide a few key examples because I think this is an interesting thing that can happen to aerosols indoors. So Chen Wang from John Abbott's group at the University of Toronto showed that if you take a limonene, key ingredient of anything that smells like citrus, and then the vapors from bleach, and you put them in a lab chamber, they would react and form new particles. Mechanism a little unclear, and this was a lab study. So we were really excited when we could go to home chem and do a test in a more field environment and show that in the real world, we know that cooking releases volatile organic compounds. So you see increases in limonene and alpha pinene and isoprene, those all increased upon cooking. And then the moment we clean with bleach, we see decreases in those original volatiles. We see a rise in oxygenated organics. And then we see the hints of a small rise in a very specific type of oxidized organic aerosol. So this showed to us, and this is really nice work from my PhD student, Jimmy Mavila, showed that we see secondary organic aerosol formation from this combination of bleach, cleaning with volatiles. But it's important to note that axis on the right-hand side shows that this fraction of particulate matter is still really small. And I think that's really driven by the very short timescales that we have for chemistry to occur in indoor environments. We have lots of other examples, but I think one that is particularly interesting to me is this study from Sweden that shows that if you take particles of different compositions and you put them into a chamber or room where you have vinyl flooring, the phthalate esters from that flooring, which are very low volatility, can actually condense onto aerosols. But more than that, the phthalate esters condense more efficiently on different types of particles. Different chemistries of particles influence that uptake rate. So this tells us again that the chemistry really matters, but this is also a method to take pollutants from one place in a house and move them around to others. There's another example that's very similar to this, but on a different time scale, and that's third-hand smoke. So the idea that someone can smoke a cigarette outside, it can move to the indoor environment, undergo processing on surfaces on timescales of months, and then revolatilize. That third-hand smoke also partitions differently to different types of particles. Different chemical compositions of particles influence that uptake rate. So here's my summary slide. We have lots of different sources of outdoor particulate matter. We have primary sources, we have secondary sources, we have natural and anthropogenic. Those undergo infiltration and then can go through this array of different chemistry, partitioning chemistry, and actual reactions, and change forms, composition, forms, and size. There are open questions about aerosol chemistry and whether that can actually occur in-house. And so I want to just end this note by providing a summary that we have lots of different sources. They're spatially and temporally variable. We have different processes, equilibrium partitioning, chemical reactions. But what we really need to do is understand the indoor budget of condensable material. What's the concentration, the reactivity, and the volatility? We need to understand what multi-phase reactions are fast enough to compete with ventilation and deposition. And we need to understand how particle composition and phase can impact indoor chemistry. So my final conclusion is that there's broad scientific consensus that outdoor particulate matter influences indoor particulate matter. So reducing outdoor sources improves indoor air quality. But we can also see that once indoors, aerosols have many chemical fates, but on far shorter timescales than outdoor air. So the resulting chemical composition is important to understand and potentially influences health. So with that, I'll thank you for your time and happy to take any questions from Kim.
Thank you for that excellent talk, Delphine.